Okay, this is the beginning of the last series of pencasts I'm going to produce. They're going to be about abelian phenomenon algebras. So before I get started, let me just make some definitions. So first, we'll say that the center of a phenomenon algebra A it's also often called set of A, but it's defined to be the intersection of A with A prime. And another definition is that a phenomenon algebra A is a factor if its center is just all the scalar multiples of the identity. So of course, A lives inside, sits inside B of H for some Hilbert space H, and of course there is a unit inside B of H, which lies in A by definition, and of course that is in the center because the identity commutes with any element of A. And a factor is then a phenomenon algebra which has a minimal center, in the sense that the only elements that commute with everything in A are the ones that are multiples of the identity. And there's, of course, there are some important examples. B of H and the n by n matrices are factors. So when I'm talking about the n by n matrices, I'm really thinking about that as the bounded operators on an n-dimensional Hilbert space. And the reason why these will give you factors is that it's very difficult to commute with all the operators on a Hilbert space, even a finite dimensional Hilbert space, because the only way you can commute with all the elements, I'm claiming, is if you're a multiple of the identity. So if you have something which is not a multiple of the identity, then it will take some vector x and send it to y, with y not being in the span of x. Right? That's what it means to not be a multiple of the identity. And if you have an operator like this, then it's fairly easy to find something that doesn't commute with it, because essentially you look at the operator which sends x to y and y to 0 or something like that, and then they will not commute. So showing that these are factors is relatively straightforward. It turns out to be a difficult question, and this is something that had the intention of von Neumann in the beginning of the theory, how many other factors there are. And so from assignment 3, you will see that there are more factors. This is a non-trivial fact, and in fact, the theory of factors in phenomenon algebras is a very important theory that has contributed to the understanding of operator algebras in a highly non-trivial way. We don't have time to go into it in this course, but there's lots of things to say. So what I'm going to do, as you can see from my title here, is I'm going to go in the opposite direction. Right? I'm going to go in the direction where the center is big. So just make it as an observation. So if A is abelian, then of course A will be contained in the commutant, because the commutant contains all the operators that commute with all the elements of A, And if A is abelian, then at least all the elements of A commute with all the elements of A. So hence the center is big, it's all of A. And my aim is to, sort of following more or less the lead of what we did in the Gelfand transform for C-star algebras, and to some extent for Banach algebras, is to characterize what the abelian phenomenon algebra looks like. Right? So this is the goal. So that's going to come over several pencasts, but to characterize the abelian phenomenon algebras. And for this, I'm going to show you an example, and then actually it's going to turn out that this example, in a certain sense, is generic. So, but we have a long way to go before we're ready to do this. So let's just think of this as an example to begin with. So what I'm going to do is I will fix K a compact Hausdorff space. And I will fix mu a finite Borel measure on K. And then I will consider the Hilbert space consisting on the L2 functions on K relative to mu. Right? So this means that the inner product of f and g will be the integral of fg bar d mu integrated over K and so on. Right? So this is the Hilbert space that I have in mind. Now let's fix some f, which is an L infinity function on K mu. Right? So what this means is that it's a function which is bounded almost everywhere relatively to the null sets of mu. And it's going to be important for us later, so let me point this out right away, that this sits inside L2 of K mu. And that's just because, if I want to, what does it mean to lie in L2? It means that the integral like this over K is finite, but I can almost everywhere, which is fine for the integral, I can majorize this with the L infinity norm of f d mu. And then, since my assumption was that mu was a finite Borel measure, this is going to be the squared L infinity norm of f times mu of K, which is finite. Right? So that means that so this is just an aside, but it sort of tells me that whenever I have an L infinity function, it's also an L2 function. And now we can define something that I would like to call MF, which I'm claiming is a bounded operator on L2 K mu, by saying that MF applied to G is Fg for G and L2 function K mu. So of course, for this to make sense, we have to work a little bit, but it's going to be relatively straightforward. So I'll just do one thing. So I mean, first of all, why is Fg an L2 function? Well, then we're going to have to look at the integral of Fg squared d mu. But just like before, this is less than the integral of the L infinity norm of f squared times g squared d mu. And then I can pull this out like this. And this, of course, is just the L2 norm squared of G. Right, so this means that Fg actually is an L2 function, and also it tells me that mf of G's 2 norm squared is the same as that. Right, so putting all this together, you see that Fg, and I mean, this also tells me that mf is a bounded operator, and you can see that the norm of mf is less than the infinity norm of f. Actually, you can prove that they're the same, but I don't really need this. And so I will set L infinity to be the set of operators that I can obtain this way. So this lives inside, of course, B of H, which is L2 for me, right? So maybe I'll write it a little bit nicer. Inside B of L2 of K U. So what I've done here is that I created a family, if you like, of operators. They're sort of multiplication operators. They work by taking a function and multiplying it on the L2 function, except, of course, the elements in L2 are not strictly speaking functions. They're equivalence classes of functions that are the same almost everywhere, but that's not a problem for what we're doing here. And my claim is that L infinity is actually going to be an abelian von Neumann algebra. Right? So this is where we're headed with this. Now, I'll make that as a claim. So what I would like to convince you of is that when I compute the commutant of L infinity, I get L infinity back. Right? So this actually tells me something a little bit stronger than what I just said. This means that L infinity is going to be a maximal abelian subalgebra that's explained in the book, but I don't really need it, so I'm going to skip it here. But it sort of means that you cannot enlarge L infinity without making it non-abelian, right? Maybe I should say this explicitly. I guess it's almost clear, but of course, the point of my construction is that it's clear that the operators in L infinity actually do commute, right? So, but maybe we can put this in this way. So, for this set containment to be true, we need to check that L infinity is abelian. And that's sort of clear, right? Because if I have mf1, mf2, two operators of this type, and I apply them to G, that's just going to be f1, f2, G. And of course, if I do this in the opposite order, mf2, mf1, G, well, that's going to be f2, f1, G, but that's the same because we're just taking pointwise multiplications of not entirely functions, but classes of functions, well defined almost everywhere relative to the null sets of mu. So that's sort of clear, but the other inclusion is not clear. So I want to prove that quite carefully. So I will fix some t, which lies in the commutant of L infinity. So that's inside B of L2 K mu. And the idea is to set G equals to T of 1. This lies in L2 of K mu. Maybe we need to be a little bit careful. So why is 1 an L2 element? Well, that's an L2 element because I've assumed that mu was a finite Borel measure. So L1 is an L2 function, so I can apply t to it. I get another element that lies in L2, and that is what I'm going to call G. And then the next step is to show that, in fact, G lies in L infinity of k mu. And when I've shown that G lies in L infinity of k mu, then there's something called mg, and I'm going to establish that that's going to be the same as t. Right, so that's where we're headed with this. Maybe I'll put the idea inside a little box here so we can look at it later. Okay, so note first that for f which lies in L infinity k mu, right, which as we've seen lies inside L2 k mu, if we apply t to f, then what do we get? Well, that's the same as applying t to mf of 1. Right? Why is this true? Well, first of all, mf makes sense because f is an L infinity function. When I'm applying mf to 1, of course I get the product of f and 1, which is just f, so that's the same. And now I can use my assumption, namely that t commutes with everything in L infinity, to see that this is the same as mf of t1. And I've defined t1 to be called g, so this is mf of g. Right, and what is mf of g? That's just f times g, or if you like, g times f. Right. So that tells me that tf is fg, and massaging this information a little bit, I will actually be able to prove that g lies in L infinity. So we note that, of course, the norm of t is the sup of t f's 2 norm, where f's 2 norm is less or equal to 1. But actually, since L infinity is dense in L2, which is a sort of a standard measure theory fact, then I can put that in and assume that f lies in L infinity of k mu. And we know what, by the computation I just did, we know that tf then is the same as fg's 2 norm, where f2 is less than or equal to 1, f is in L infinity k mu. And now, I hope you'll allow me to be a little bit sloppy here. So you can use this to conclude that g is an L infinity function, simply because when you check, if you want to check that something is an L infinity function, you can multiply it up against all the norm 1 f2 functions and see if that is bounded. So essentially that's the same as my argument that I skipped, that the norm of mf is the same as the infinity norm of f. So using this one may show that g is in L infinity k mu with the infinity norm the same as the norm of t. But then we're done, right? Because now we know that t applied to f is the same as mg applied to f for all f lying in L infinity k mu, and that is dense. And now, since of course t by definition is bounded and mg we've checked is bounded, then by continuity this is for all f, right? So t is going to be mg, and hence it lies in L infinity, which was our goal. And then finally, write that as a corollary. L infinity is a von Neumann algebra, simply because to check by the bicommutant theorem, we need to check what happens to the bicommutant of L infinity, but that is just by definition the commutant of the commutant, and we've proven that the commutant of L infinity is just L infinity, so we can just do this twice and come back to the original subalgebra.